The second day. So hello everyone. I appreciate you coming in on the second day. And basically, this session is going to be all practical. So there will be no theory, no PowerPoints. As a matter of fact, all the courses that I give has got minimal PowerPoints, and most of it is all practical. The working medium we will be working in is what you see on the screen here, which is VS Code. I'm pointing at this little logo. VS Code has gained popularity amongst programmers. It's for free. So you download it, you install it, and that would be one of the packages we will install for you when we start the course. And basically, on the left-hand side, so I want to make clear, this is not the real training course. So I will go through some of the points quickly, and I will not wait for you to understand, but I just want to give you a glimpse of what you will be going through in the course. So in geology and geophysics, or in geoscience generally speaking, we deal mainly with logs, well logs, drilled well logs, and seismic. The medium of dealing with well logs is going to be LAS files, which is the log ASCII standard. And everyone knows LAS files. Most or all contractors or companies, that service companies, they supply you the LAS files. Most software export LAS files. So if you have Petrel, it's very easy. You push button and you export your LAS file. So there's no issues there. And the seismic part will be dealt with as SegWi. And the reason I've done it this way is that also Petrel and all packages, you push the button and you take your seismic, export it into a separate file, and the extension would be SegWi format. That is then readable by this course and any of the other packages, whereby we will manipulate those files, generate new LAS with new data, or generate new SegWi with new data, and then you can read it back into Petrel or Landmark or anything you're working on. So that is the methodology we'll be following. So when we go into notebooks, basically on the left-hand side, you see the tree, which is each one of those is a directory. You can push. I hope you can see my cursor. You just click and you open up all the files under it. So we are now going to focus mainly on the LAS files. So LAS and SegWi. So I hope this hour would fit both. But mainly, let's get started. So this little icon here, we will simply click on it again. It's a toggle. You either get this list, but that's taking much of the screen space. So I will click it like this. So then I can actually zoom in for you to see for visual aspects. So what we'll do here is simply, this is a cell. When I'm clicking outside the cell, this is still a cell, but inactive. If you see here, when I hover my cursor on the cell, you see three things showing up. So there are, forget about generate. This is a new option we're using AI, but the cell could either be code or markdown. Okay? We will not get to that distinction right now. The markdown is something where you write text in like that with bold and whatnot. Just to give you the good news, the Jupyter notebooks have been used to write books. So a lot of universities are now supplying their text in Jupyter Notebook because they can write text like this and have live cells working. As you can see here, there is the word Python. This cell, it understands that you're typing Python. Now, I'm taking my time to interpret this the first time, but I will not be interpreting it at length in the subsequent notebooks. So what we need to do, the first thing you need to do is recommended, is to import the necessary libraries. By the way, OS, the library OS, as you can see when I hover my cursor, one of the beauties of VS Code, it gives me a help. And I can go in, you don't need to go into Google or anything like that. You can see all the help, whatever comes out in Google is already built in, and you can read what that library does. Like when I hover over here, NumPy, and you can go to NumPy Home. It even has hyperlinks and give you example of how to use it. So it's quite amenable and friendly to users. But obviously, it gets a bit annoying when I hover like this, and then something shows up, and we're not interested in. So the libraries we'll be using, the standard libraries is NumPy, and we will import it, give it something called an alias, like a nickname, just to make it short, NP, pandas, PD, and then matplotlib. So we import those libraries because we're working with logs. Our main library that we should have installed at the start of the course will be las.io. So while I'm inside, see, when I'm clicking, I clicked inside and suddenly this thing got activated or the color changed. When I click outside, yeah, I can hover in there, but it's not active. And you can see here that this blue bar, if it gets thicker if you're on it. What I do is if I click on it, it's reduced to a line, but it's giving me this little thing saying, and these three dots saying there is more to the cell. It's not only one line. If I click again, it opens up. That saves space on the screen instead of scrolling up and down, especially that these cells can grow considerably big. So when I go in here, click inside, and I type Shift Enter. This is how I run it. And it gives me a sequential number because I started this notebook before we started. So now it's in cell number 7. It keeps a count. So we have a directory. Let me open up here. We have a directory called 04 last. I mean, that could be like an explorer. You can use this as an explorer, Windows Explorer. So we have lots of wells. I have given you lots of wells, and these wells are downloaded from Australia. So the names would be odd. But anyway, the last file usually has a .las extension. So there are many last files that I've given you in this data set. So we want to be able to read them all and see what's inside those last files. So what we need to do is, I have supplied you a program. The code is available for you, by the way, and let me show you. Which is called dirlistlas.py. This is a program that I've written. It's very simple. So it's for free. I've given it to you. It reads everything that's called las and then gives you the comparisons, and I'll show you what it gives you in a second. But let me just drag this here. And now I'm going to open on the right-hand side to save on the screen space. So that is a program that I've given you that runs, and this is the code. You have the code. Once you go through the course, you'll have the code as an example, and then you can run it as is or change it or learn from it how to read and manipulate LAS files. So this is the code. It's just for showing you what that is. I will close this to save on the screen space. Now, what we'll do is there is something called a magic, so not a, there are some things called magic commands, and one of them is run. So within each cell, it can work like a terminal, and I can run many programs within the cell. All what I need to do is precede it with a star, with a percent sign, percent and the word run, no space in between them. And then you say, name your program. So it's dir list flash. And you can, from the name, I mean, you can call it anything, but I called it directory list, all the last files. And dash H is just to give me a help. And I'll run this, and basically it shows me when I ran it. Now this is cell number 8, and this output there is a POSIX format. Forget about this term, but it's coming from Linux, and that's the standard CLI. I'm giving you a lot of terms. There's no time to explain them, but I would hope that when you get the recording, you can then Google these terms and find exactly what I'm talking about, because there's in the course I will explain all this. I'll take my time. That's why it's spanning 10 days. So this gives you how to use it. Basically, we have dash dash version and give it the version number, and then the out there. Where do you want to get this file generated? So we will run it again. So you could either copy, use this, like go in here and then highlight that and copy that without the dash H, or I just typed it again. And then I said, give me a version, because I already have another version in your directory. So I don't want to mess it up. So I have a version 01, and then out there, dash dash out there. Where do you want it out? I simply go, and let me show you this, because you will need to learn that. Uh, where is my Explorer? So here is my Explorer, and basically this is the same directory we're on. This is 04 LAS, and this is the PEA course that I have structured there. So what you do is you go onto the address bar and you click, sorry, you go into the address bar and you click. So it's already highlighted. What you do is Control C and go in here and say Control V. I already have it done, so I'm not going to do it again. Okay? Now, so we run this. It's going to start giving me some output. It's processing each log. It's processing and it's saying successfully generated proj wells V01, and the second log successfully generated. So it's the first time it says generated, the second time onwards it says appended. Now VS Code is very nice because obviously it wants to save space. So by the way, this session isn't designed for explaining how to use VS Code. So I'm just going to tell you all the text that was generated. You can open this, and another text editor is opened, like this one. And this is actually all what came out. And you can see each well named Poseidon 1, and then well named Poseidon 2, one named Poseidon North, and it gives you all the details. And look at these tables that's coming out. So I will click on this. It's always accessible to you if you click on text editor. Now, what happened is, and as we can see, we just refresh that, and we will see that there is a file called proj wells. there should be a file called proj wells. Where is it? Okay, there is the old one here, but the new one should have come out. Let me check. Yeah, okay. So we will take projwells 01. It's been created now. We will then drag it into VS Code. And you can see the dashed rectangle. I will put it into the right half. And this, so that's what comes out. Wow, that looks ugly. We need to take it into Excel. No, please don't use Excel. Here is what you need to do. I will install for you a package called preview, which then when I right click on the title, it will give you a preview. Now, this is almost like Excel. You can't edit, but you can filter. So for instance, if you want to have, this is the file name. So these are how the Explorer file names look like, but this is the well name. So now we can see all the well names here. Let's say I want to look out, I'm interested in the one called Torosa. So I'll just switch off all and then apply. So I'm only left with that, identical to what you do in Excel. We're not trying to reinvent the wheel. We're trying to get everything done in Python environment, because that's a lot quicker and easier than having to save files and answer questions. Are you sure it will not say the format and all these kind of things that come with Excel? Here is what we're looking for. We're looking for, in this well, what are the curves that are available? So it's got gamma ray and the names, the mnemonic. These are called mnemonics. RS, RD, so resistivity, and then BATC, well, I don't know what, and DTS, so sonic, shear sonic, compressional sonic, and so on. Now, it also gives you the statistics you definitely need. So you need the minimum depth and the maximum depth. So most of the wells start from 500 and ends around 4,000 or so. That's meters, by the way. The project, these are very deep wells. Nevertheless, there is this Torosa 1, this curve starts from 34. So now you can mentally visualize that this is a very short interval. All those starting from 34, 35 are very short intervals as compared to the wells, to the curves starting from 600. So now you get the feel for how long these curves are. Some wells have only short interval. So you understand now the statistics, and then you can go in Vmin, Vmax, the value actually, what's your minimum. Now gamma ray, can you believe gamma ray as Vmin 7 and then 695, yeah? That's obviously an anomaly. So that means you as a data analyst, you'll have to go in and edit this spike. There's a weird, several weird values, I don't know. We have to make sure to edit those, okay? And so on. So resistivity, yes, goes in the thousands, that kind of stuff. So I just wanted to give you a feel for how you can navigate your data. Now, let's say we want to go for select only, let's say we'll check the gamma ray, apply, but then for these wells, we'll go for and select. So basically, when I do that selection, wow, only out of all those wells that we had, we only have 3 gamma rays. So even though it sounds like we have 9 wells or 12 wells, we only have 3 wells with gamma ray. So now you're able to figure out what your data is, and that is your responsibility as a data scientist. When you do machine learning, you want to adopt the role of a data scientist. And that's the first behavior of a data scientist. Understand your data, understand your limits, how many of those, and whether it's worth to build a model on 3 curves only, and so on. So I will close this and move on. So just to give you an idea, PWD is print working directory. It's a Unix or Linux command, but it works in Windows also. So this is where we are. You can recognize the 04-las. And then there is also this command, which is the OS command, which is within Python. Get CWD, get current working directory. Now, get current working directory, it shows this. Now, here is where the action comes in. Within Python, we don't need to go to Explorer. We can simply type OS, as the name says, list dir. So that this is a built-in function. It's not my program. It's built into Python. So you say OS list dir, and I type this, and these are all the files in the directory. Please note, when you see those 3 dots in Python, we call them ellipses. When you see those, that means there are some things that are, because of the memory constraint, they did not display, but there's more. If you still desire to see them, you can click on this text editor and it will show you the full list. Okay? That's what's in the directory. Now, we would like to read, now let's be serious. Now, we would like to read one well. So I selected Proteus1 decimated.las. So here's how we read it. Now, pay attention. Now we're getting into the G side. So we say lasio.read, and we output it to something called var. Nothing happens. Okay? Then we go in, we say print var.well and print var.other. And by the way, print has to have parentheses. It's a function. It's a method. So we do this, shift enter. Now, here is what we get. So when I said yesterday, please don't take the liberty of modifying the metadata, the header that comes in the last file, I meant it, because we read all those and you can recognize this is the header of your last file, the start, the stop, the step, and the unit is in meters. Here is that thing, and the step is so and so. The null is -990. A lot of people, I get a lot of data from companies where they say, oh yeah, we'll just say null or say 0. No, you have to keep it -999.25 as your null, because there are programs that assume so. Now, this is by Schlumberger and whatnot. Anyway, so that's not very useful to us. So one of the major commands we will be doing with every well is to convert it to a data frame, to a pandas data frame. Now, obviously, we did not, through the course, you would have gone through what is pandas, what is a data frame, what are series, and then you would understand what I'm talking about. So I'm not going to dwell much. I'm just going to say, okay, let's convert it to a data frame and display its head. Head meaning the first 10 lines. So what comes out here is, this is a nice, like a spreadsheet with the header, gamma ray, RS, the ones that we saw when we inspected the files, and then DEPT, which is the mnemonic reserved for depth. They don't use depth as 5-letter word. It has to be this 4-letter word, DEPT. And this is where it starts from, and it's every half a meter. So that's easy. Now, we would like, in order for us to process in Python the logs, we would like, if you see here, DEPT has got its own line, meaning this is an index. I don't want it to be an index. I want it to be the same level. So what we'll do is we'll just simply say reset index, and now everything is nice. And some of the decimal places is a bit ugly. So how to get that is you can simply use something called the chain command, which is instead of we could have done this instead of tail, I could have typed in dot round, and I could say two decimal places, okay? And then shift enter. So now everything is 2 decimal places, okay? What was originally 1 was kept 1. Okay, now we will go for, there's a famous command which is called describe. And as a data scientist trying to work machine learning, that is your friend, because it gives you the count. So obviously, wow, the index has 9521 counts, meaning there's obviously no such thing as a missing index. The index has to be, this is your file. It starts and ends. So we have 95,000 rows. And the depths also 95,000 rows. Fair enough. But then gamma ray has 93. That means it's not the full range. Now, when you look at shear, DTS, the shear sonic, it's only 300 values. So you have a tiny little bit of shear sonic recorded. When you look at row B, it's only 645 compared to the 95,000. So there is this range that's very short, and this would give you an idea as to, oh yeah, I can make a model, but be careful. The shear model is only going to be, or at least in that well, the shear values are going to be very small, very little. It also gives you the mean, standard deviation, and these terms you have to, in the course, we will expand on what the real meaning. I'm not interested in mathematical definitions. What does it mean and how does it impact my work? That's basically what we're doing. We need those statistical terms to see how it impacts my decisions, because based on that, I'll make decisions, use this model, and these are the parameters that I want to use. So I'm not going to expand on this. We will expand in the course, but finally, let's see if we can get a plot. Now, if we gone through the matplotlib course sessions, you would understand this, but this is the best way of making a plot. So we're saying plot the DEPT against gamma ray. Now, that's not the way we look at logs. We need the depth vertically, and we need the values horizontally, the log values. So what we need to do is swap the gamma ray with the depth and say invert y-axis. All of that I go through quickly in the course because we've spent time in matplotlib to understand all that. So forgive me if I'm not spending much time. So now these are the gamma ray values, and this is the depth here, and the depth starts incrementing from 0 up and going down as we go along. Okay, that's nice. Obviously, and let me just stress a fact. I am not trying to compete with Techlog or Schlumberger plots or anything like that. We're just trying to plot in everything within our environment so that we can make decisions. Not tell you, okay, look at it in Excel and then come back. That's very inconvenient. So now let's see if we can I'll skip this cell, but now we simply type, we simply look at all the files. Here is a small code that I read all the files, select only the ones with LAS, okay, which is duplicating dir list LAS. But I just want to show you, here is the smaller code. Give you the well name and give all the mnemonics in the head taken from the header. Okay, so we will just run this. It's reading all the wells. I think it's finished. And here is the output. So you can see, like, it's like a compilation of all the headers. Now, I don't do this in dir list LAS. I only read what's relevant. So the first well is boring. This is where the name of the file, and then I read the well name. It's written somewhere in here as the well name. Boreas 1 is the well under this code, and so on and so forth. Okay, so that's where I will stop at this point. Now we will go for the next. We will go for the next. Here is now we need to do. You remember when I told you you have to do EDA? We will take some wells and do exploratory data analysis. So the first thing we do, and you should do, is select your kernel. So EDA is essential. Now you understood basically statistics, but you need to understand other statistical terms and plot them. So here's what we need to do. These set of wells are different from Australia. These are from the North Sea. So and we import, as the first cell, we always import. We will import Seaborn also, which is a plotting library. So I had previously read those wells from the North Sea, and see, and if it's running, it gives you this roaming cursor, but then now it's finished, so that now you know it's finished. So then I go in, Shift Enter, there's nothing there. It read the data files, so and it read them into what I call W0DF and W1DF. These are variables. You'll understand all that once you know pandas. But anyway, so if I look at the columns, you remember the columns? The column, the header gave me, there's the facies, formation, well name, depth, gamma ray, and not whatnot. So I make a list, and a list is anything that you will learn on the first day. What are the different types of structures in Python? Anything in square brackets is called a list. So we make a list of items that I want to keep, and this is what we do. So that is the list, and this is how I filter it. Now I then concat those two together, and then because this thing is called well space name. My advice to you: never use not never. I mean, it's better not to use pandas with column names that have spaces. It's going to limit you in terms of usage. So I am renaming here well.name to well, and this is the format. I can't spend time explaining what that is, so I'll just do it. And this is now the header of this file. Now, how many wells do we have? Well, this is the command dot unique. So WDF, we have a column called well. So we'll use the chain command. the data frame name dot, well dot, and then unique, and unique is a method, so it needs parentheses. And we do this and we get this list here. So we have a well called recruits. I mean, all the well names look okay. We have a well, I'd like to drop it. So here is how to filter it out. You just simply use this command, the WDF square bracket, WDF.well, and then exclamation mark equal. All of that is Python syntax. So we should have covered that in the first session, but let's follow along. Now, and then we go for unique. Now, sorry, n unique. Now it gives me the number of wells we're looking at. We have 9 wells in this database. So in this data frame, sorry for the misspeaking. And then we save it. This is how to save it to a CSV. And you say index equals false. Now we read that again. We convert our columns to list. And then we print the list. You notice here, you notice when I said print, it's printing W list in a square brackets with items in between with and separated by commas. That's the definition of a Python list. Now, if we type in the head, this is a little command here. So now we have 9 wells. So what I'll do is I'll do this for your, you can left click on these 3 buttons and say clear cell outputs. So I can go, so what I'm doing here is I'm generating a plot for each well in this list, these 9 wells that we looked at earlier, and I'm plotting that column against depth. Now let's see how that works. And I've made the figure so wide, I didn't want to, obviously from now on, things will take a long time. It's plotting each well after each another. Okay, it's finished. So we have the logs here. Sorry, the log type here, and we have PF, and this is the one name put on top, and the depth only listed to the left, and you can see the curves. Now, I could, for you to see better, well, let's keep the zooming like this. I don't want to mess this. So here are all the wells plotted. So I don't want to spend too much time on it. There's nothing new to see here. Now, the next thing is, what do I do? Okay, so I plotted those. The first thing you do after just plotting your data is to go for univariate exploration. Now, the variables that we have, each one of those log curve types, we call them a variable or a dimension or a feature. All of these are synonymous terms. Now, univariate meaning I'm trying to analyze each column on its own, regardless of its neighbor. I'm not doing anything to see the relationship between the first and the second column. I just want to see what's in the first column, what's in the second column. So the first thing to do is to plot histograms. And then plot something called KDE, line 6 here. KDE, kernel density estimation. And obviously that's a statistical term, but we will go and explain what it means in the course. And you need to know it, by the way. So don't say, no, I'm a machine learning expert. I don't need, you definitely need to know that. You don't need to know the math behind it, but you need to know how to apply it and why are you applying it. And when it gives you a certain shape, What does it mean? All of that we'll cover in the course. So anyway, we'll do this and run them very quick. I'll clear, I'll left click, clear all outputs, and rerun this again. So you can see the cursor up here. That's one of the beauty of VS Code. It's anywhere you go, you can see that this cell is running. So when you see this roaming from left to right, now it's still running. It's plotting, it's generating its plots. So let's just check this well here. The last one. I mean, it plotted for everyone, for every well. But let's just check this cross cattle well. The gamma ray, what are we trying to inspect here? We are trying to look at the histogram. This little pinkish curve or red curve, it should be red, but I don't know, the screen comes out pinkish. This is the KDE, kernel density estimation, okay? From which we would generate PDF, the probability density function, from which we will then create a CDF, cumulative distribution function, okay? And these three are needed for us to do numerous things in machine learning and in Bayesian work and all that kind of stuff. So what we're looking at over here, it looks normal distribution. The normal distribution would have a central peak with mirror images on both sides, even though it has a tail. So you could say it's a bit skewed. Now the skewness is by tail, it's not by peak. So here we call this a right skewed, okay? Even though the peak is skewed, is pushed to the left, we don't call it skewed to the, we say skewed to the right. So this is a normal distribution for the resistivity. The delta phi is definitely left skewed, and the phi nd is definitely right skewed, and so on. So you get a mental vision of what your data, how you need to handle your data, and also the ranges. So the delta phi on the negative side is very high. Maybe you want to chop it up. Maybe you want to say I need to remove anything above 120 or 130. All these values, all the up to 150. It's your call as a data scientist, stroke geoscientist, because you now are the most capable person that can make a decision. Do I need to chop off these low values, the sandy values? Should I kill them and say that my well doesn't have sand? Well, it's your call as a data scientist, stroke geoscientist. So let's move on. I'm just giving you a sample of what you need to do. Now, with Seaborn, look at how ugly the histograms were. But with Seaborn, we get a better looking, it's just a viewing thing. So I'm not going to go through that. Now, there is something called box plots. Wow. Now, box plots is something you want to know the ranges of your data. So I will simply clear these cells and run this cell. And it takes each column on its own. And okay, so what we're seeing here is, for instance, if you relate mentally to the phi and d, you will see that there is a box here. This is the mean, and now it so happens to be the median. So that's the median and that's the mean. And you can see that is the P25. If any one of you in the oil industry would probably mix with reservoir engineers and they're obsessed with P10, P20, P50, and P80 and whatnot, that's the P25 and that's the P75. So that's the percentile, the 25th percentile. This is how you express it. And the 75th percentile. This is the P50, which is the median. The P50 is the median. All of these little dots, circles here, according to statisticians, are called outliers. So if you give your data to a statistician, he will have the license to remove all those data because we have something called interquartile range, which is the range between P25 and P75, and multiply that by 1.5, and that's this whisker. That diagram is called box whisker. So you go in and Google that later on and you find all those definitions. But you, as a data scientist coming as a geoscientist, you say, no, these data are important. I cannot remove them. And so anyway, we'll move on. I just want to go to another notebook very quickly, but we'll move on to how do we generate now multivariate. So that's multivariate. What is the relationship of these data? So I'll make something called heat map. And it takes a long time, but anyway. So here's one well, for instance. I'll just zoom out a little bit so that you can see what's there. Come on. Yeah. So each well will have all these curves on the x-axis and all the same curves on the y-axis. So in essence, along the diagonal, you will see that PE is with PE. So on the x-axis, on the y-axis, you will see obviously ones, meaning the correlation is perfect. Yeah, when I correlate something with itself, the correlation is going to be perfect. But correlating PE with phi and D, it's a negative correlation, but it's 0.5, so it's reasonable. This is very low, and so on. And that's how you read them for each and every one of those wells. And now you can find where there is relative correlations. Now, I want to very quickly zoom in again for you to see, and I'll go here very. So what we need to do is we will. Okay, I have about 15 minutes left, and I need to cover. I will not. Okay, no, I will cover this. So here is how I open a new notebook. And we want to go and do some machine learning now. Okay, where am I? I think I need to say Control Home. So we will do linear regression with Python. So the first thing is, yeah, okay. We'll import the libraries. You already know that now. We will be importing CatBoost Regressor and linear regression, okay? And we'll be importing the metrics. You remember when we talked about the R2 score, root mean squared error in the previous session? So it wasn't wasting your time. It was just for you to recognize what's happening here. We will read the log data that we saved in the previous session. So here's the log data. All the well names are in here, the depths and all the curves. And we will say that the last column, here's the terminology, is our target. And GR, ILD, delta, whatever, phi, D, and all of these are called features, okay? Or dimensions. So those features, I will use those features to predict PE. So, and we will then generate a list of wells, W list. So here is the list of wells, and we will extract the relevant columns. We will extract what we call a trained data set and a test data set. Here I have to stop and say, in normal machine learning, this is one of the main differences between a normal machine learning and our geoscience. In geoscience, we prefer to hold out wells. In other data sets, like financial or whatever, they want to keep, it's random. I just hold on to random selection of my data. But here we have to order them by wells. So we keep 2 wells, 4 wells, and run the rest, use the rest for training. So we created a train and test, and then, okay, we run the cell. So we have 31 or almost 3,000 in the train and 830 in the test. So we will assume PE is our target, okay? And we will then generate the data, stripping off extra stuff. Okay, we'll do this here. Now, we already split the data, but we're not gonna, okay. Here is a function I have given you where I plot the wells. So I'm not gonna go to all, but the code is there for you during the course and after to modify and edit to your liking. But you will see how that looks. We will just run the cell. Now over here, I'm giving you what the definition, there's no time for that. So we will go for the first model, which is cat boost regressor, which is what I feel is the most optimum regression model. But you can debate that and try different stuff, and I'll show you how easy it is to try different things. Here are the critical parameters. So I separated them in a cell. This is the beauty of working in a notebook. Each cell is separate from its surroundings, but obviously the sequence of the cells matters. So iterations, these are the three critical parameters: the iterations, the learning rate, and the depth. So I gave it 1500, learning rate of 0.8, 0.08. The learning rate cannot be more than a 0.99. So from 0.1, sorry, 0.001 to 0.99. So it's almost from 0 to 1. So that is mid-range, and I'm using root mean squared error, and I'm just saying don't display anything on the screen. So here is how you set up the model. Literally, this is how you set up the model. Just say learning rate equals, depth equals, random equals, and then say model.fit and give it the scaled version. Did we run the scaled version or not? I might have missed the scaled version. I'm not sure. So let's just do scaling just in case it doesn't, so I don't have time for any errors. Okay, now, so let's fit the model. I basically, and here is the cursor that's going like this, telling you it's running. It takes time. Finished. Okay, and it gives you that, which is nothing for us humans to know. It's if you want to do debugging, you go into that where the model is stored in your memory. Now, let's do prediction on the train, and we will do predictions. That's all what it takes. You simply say CBR model.predict and give it the data. And then we will give it the test. here is the data scaled train, here is the data scaled test. And then we'll just run the cell. That's all what it takes. So now we have generated the W test DF. So we will then use that function, that long function that was previously showed, and say plot wells pred and give it the data frame that I'm looking at. So let me just, I need to zoom out so for you to see. So here is, so we held out only 2 wells, and here is the prediction. The dark is the actual PE, and the red is the prediction. So it's not really doing good with that, but can we try some other parameters? I'll show you very quickly. If you change some of the parameters, so let's say, okay, how about changing this to 0.5? And here we'll say 5. We run this cell. We refit the model, run the following cell. And your eyes should be focused up here, because if there is a roaming, yeah, it's finished. Now, we run this cell again to create the data, and then we go here and run the cell. So let me just, so it's a bit noisy. It's got some over the reservoir, it's able to actually reach the values, but it's got some weird peaks and troughs here. So you can keep on testing up until you get the right parameter. And that is machine learning in terms of logs. You have to test, you have to keep on testing your parameters. But now that is going to be tedious, isn't it? To keep testing. That's why we have something called cross-validation. Now, let me just show you this cell here. I hope this is zoomed in enough, yeah. So we now created a new column, and I called it CBR, cat boost regression, PE. You can call it anything you like. There's no restriction. Now I will create a residual. What is the meaning of a residual? I subtract actual minus predicted, which is here. Actual minus predicted. So I'll run this, and then to make sure that your residuals are correct, you need to run this command, this plot, and let me just zoom out. This is basically a histogram, but plotted horizontally. And what you were expecting is that your data should be at 0. Your maximum, sorry, should be at 0, petering out at the flanks. You look at where your, yeah, okay, so I have maybe minus 1.5 to 1. This is my range of errors. And these are the units of your data. So to make sure that everything is okay, we run this cell, which is another way of displaying your residuals, which is your actual is on the x-axis and your predicted is on the y-axis. And then this is the 45-degree line. Ideal situation, the blue dots should be on the 45-degree line. But when you look at this, there are two terms I'd like to introduce you to: homoskedastic and heteroskedastic. When the cloud should be hugging your 45-degree line. So when you look at this, so people are saying, okay, yeah, I just generate these in Excel, but what does it mean? Well, you have to interpret these plots. And one of the interpretation is, okay, if the data spreads from the 45-degree line is very significant. We need to get that cloud closer to the 45-degree line. And if your data is, ignoring this portion and that portion, because these two are extremes, that your data, it looks like you can draw a cloud, just a blob around it like this. This is called homoskedastic. If you had patches like this out here and patches like all your data on the low end is above the 45-degree line and data on the high end below the 45-degree line, you could qualify this as heteroskedastic. Having said that, this is not just sophistication in statistics. This is going to be a criteria you use to choose which model you need to apply. So you need to analyze what your model predicts and interpret that to be able to say, is CatBoost or are these parameters good or not good? Okay? So it's not simply looking at a number. Oh yeah, RMS is good. No, you have to evaluate them you have to interpret these plots. Now, obviously, this is plotting so in essence, when I did the training, here is what the training looks like. The training is meaning the data that it saw to train on. So it should come out perfect. So that is the range. This is acceptable when you have it's sort of like hugging, even though there might be a trend here because on the high end you have the data on the low, but on the low end I guess it's fitting on the 45-degree line, so we're not complaining that much. So your model doesn't. Anyway, there is linear regression, and I'm not going to go through that. There's not enough time, but I will just go for just to show you how do I set up my parameters. This is the concept of cross-validation. I'll leave you at that. We will expand on this and apply it in the course extensively. But here I just wanted to show you that if this is the span of all your data, we then, if I say 5-fold cross-validation, I break my data into fold 1, 2, 3, 4, and so on. And then I take fold 1, hold it out, okay, and give the training fold 2, 3, 4, and 5, okay, and then do the prediction like we did just a while ago and come up with a metric. We do the same thing, but now fold 1 is in, fold 2 is the one held out. So if we held out 2 wells in the geoscience field, if we held out 2 wells, the next time we will hold out other 2 wells, not the same 2 wells. And the third time we hold out another 2 wells, and so on up until we exhaust all wells have been hidden, so that we don't get lucky and hold out the ugly wells and our prediction comes out good. So I just wanted to, and then we might also do repeated k-fold. So we don't do it once, we do it like we held 2 wells in a row. Well, we're not going to have those 2 wells. We'll have this well now and another one randomly selected. So That way we ensure that our results are optimum and we can defend them to our managers and to our company that these results are robust. So it's almost time for the end of the session, but I would like to show you another model that is of significance, which is random forest regressor. Now, random forest is based on the ensemble model, and in it, and in the course, of course, we'll go through two terms you need to know. And please Google them, even if you're not going to come into the course, Google them and to know what is boosting and what is bagging. And bagging has nothing to do with a bag. It's a combination of the word bootstrap aggregation. So there is a word called boosting and there is a word called bagging. And this constitutes the essence of ensemble models. So we will go through that and explain it, not mathematically, explain it so that your takeaway message is, I understand what it does. I understand what the difference is between XGBoost or CatBoost versus random forest. And I think there is just one model here, which is support vector machines. And support vector machines is basically trying to find a plane that separates the data. And it uses vectors to identify those two, like the ceiling and the floor, so that it doesn't collapse onto that feature. And basically it's like that. So we go through I know it's too small. We go through and I give you all the text here in the notebook. Now, by the way, if you don't like these showing up, you can simply switch them off and you'll see you can condense them. So we also test out this support vector machines, and maybe they have some better results that you like. So it's very easy. It's just shift enter 3 cells, and the plotting is another 3 cells, and that's it. You filled many models. So the question yesterday, can we do this in research? Absolutely. You have your same data set. After you put them in a CSV, you try, there are at least 50 odd models in scikit-learn, and we will be loading other models like CatBoost and whatnot, and extreme gradient boosting, and you can try all, and then neural network. There is no, the sky is the limit for neural network. And you can try neural network to your heart's desire and compile all the results and present them, make a conclusion, of course, and then present your conclusions. And to make a conclusion, you need those QC plots. You can't simply look at a number. I'm cautioning you, even if you're not attending the course, please don't apply machine learning. Look at your RMS amplitude or mean squared, mean absolute error or something like that, and say, oh, I'm happy, this is good result. No, you have to run your diagnostics of your residuals. You can't simply skip that. And at that point, I will have to end the session. I wanted to go into seismic, but just there isn't time in this session.